All right, we're going to be going over sections 4.1 to 4.5. This is going to go over derivatives as a whole. Right. Now, to start off, as a base, what is a derivative, right? A derivative gives us the instantaneous rate of change of what's going on in a function at a certain point, right? And so, the formal definition of a derivative, as I've kind of talked about in the previous video, is going to be the limit as not x this time, it's going to be as h approaches 0 of f of x plus h, extend this out a bit longer, f of x plus h minus f of x all over x plus h minus x, or say this as the limit as x approaches h of f of x plus h minus f of x over h. That one's probably a little bit more familiar. Right. So just keep that in mind. But I'm really not going to be touching upon this formal definition anymore. We're going to be going over a couple more key tricks and ideas that'll make it much more easier to find derivatives. But before doing that, we're going to go over how do you prove it being like you're trying to find your continuity and your differentiability, right? So let's write this down. Proving differentiability and continuity. So let's start off with our first example when it comes to this, right? Let's say Let's say we have the function f of x, and this is going to be a piecewise function where, mm, say, 2x squared minus 3x plus 1 is going to be when x is less than 1, and then we're going to have the function be 0 when the function is equal to 0, and then we're going to have it be x minus 1 when the function is greater than 0. Right. So the first thing that we need to do, right, is what I'm gonna make is I'm gonna call this a little checklist box, right? Set this up here. We're gonna have continuity here, and we're gonna have differentiability here, right? So in order for this to happen with continuity, like we talked about in the previous video, we need to have the left and right limit agree, right? So for our checklist here, let's just put left on this part, put right on this part. And then we also remember the value at whatever point A we're talking about needs to also be the same as the left and right limit. So let's put point value this out. Here, hold up. We move this one higher. Let me just move this one lower. Yep. And this out here. Clean this up. What we need to know is for our function to be continuous, we remember that it has to be the left limit agreeing with the right limit, and our point value has to be the same, right? We can this out. Right? And so if we know that, then it's going to be continuous. We also need our left and right side derivatives, they also need to agree with each other. And if we have that happen, then we know that it's differentiable, right? And so that means it's going to be continuous and differentiable, right? But if we have the left limit and say the point value agreeing, but the right limit doesn't agree, that means that it cannot be differentiable and it cannot, well, yeah, it just can't be differentiable. Right? So the key thing to remember here with this little chart here is that in order for a function to be differentiable, it must be continuous, right? But it doesn't go the other way around. It can't be differentiable but not continuous, right? And if you remember this chart, this goes over everything that you need to do to prove it. So if we go back over here to our little example problem, the first thing we need to do is, what does our checklist say? We need to take the left right limit and the point value. So we'll take the limit as x approaches 1 from negative infinity. If we look at our function here, that's going to be 2x squared minus 3x plus 1. We take it 2x squared minus 3x 1. Yeah. And we're going to just insert our 1 and see what happens. Okay, so we get 2 multiplied by 1 squared minus 3 times 1 plus 1. That's going to give us 0. So boom, that checks out. So now we're going to evaluate our right limit. Right limit, which is 1 from positive infinity, is going to be x minus 1, right? And x is going to be greater than 1. So if we plug in 1 here, just 1 minus 1, that's going to be 0. So now we see that our left and right limit agree. So now we need to check our function at the value of 1. And it tells us that that value is going to be equal to 1. So we can say that of 1 is going to be equal to 0. So we can say that since the left limit and the right limit and the point of the value both agree, we can say that this function is continuous, right? We can put this here. Okay. We can say, yes, it is continuous. Now, the next thing we need to check for is differentiability, right? So in order to check differentiability, we now have to get the derivative of this whole set. So let's do f prime of x. This is going to be 4x minus 3. The derivative of 0 is just 0, and then the derivative of 1 is just 1, right? And so these are for the same bounds here. When x is less than 1, x is equal to 1, x is greater than 1. So for this one, if we look back at our checklist, actually, let's just cross this off here. From what we got here, we say that the left limit agrees, we say that the right limit agrees, and our point value agrees. So let's go and evaluate here. Let's take here, we have our derivatives. So now let's plug in a 1 into this one right here. So let's see. Our left side, when we plug in 1 minus 3, we're going to end up with 1, right? So we can come here, back this off. And then when we plug in 1 into this, there's no x variable. So that just also means it's 1. So we can then say that our left side and our right side of the graph do agree with each other when it comes to being their derivatives. So we can check this off, and then we can combine everything that we just did together and now say that this function is differentiable. Boom. It's just that simple. Now that we've done that, we can now get into the other fun stuff about derivatives. We can now go over the product rule. So the product rule states, it's saying that looks a little ugly. Fix that. The product rule then says that if we take d over dx of f of x times g of x, you're going to end up with f prime of x times g of x plus f of x times g prime of x, right? And so pretty much just got to remember that. Let's get on the answer sheet, but it's not that hard to remember. So let's get into some example problems with them. So let's say we have this function h of x here, right? And it's going to be 3x minus 5 multiplied by x squared plus 4x. And we want to know what h prime is. So the way that we would go about this is how I at least envision it, is I break this down. I want this part to be my f of x function, and I want this part to be my g of x function, right? Doesn't really matter whatever one you do, doesn't matter. It's just only for your brain to help, right? And so then you can now break this apart and say, I want the derivative of this part here, this 3x minus 5, and then this is going to give you 3, and then you can take the derivative of your other part here, of your x squared plus 4x, and then say that, okay, this is just 2x plus 4, right? You got all that. Now you have all your pieces here now. This is your, if you look back here from where we assigned it, this is your f of x. This is your g of x. Well, g prime of x and f prime of x. So all we have to do here is then, from what we have in our product rule, take our f prime of x, the 3, multiply it by the g of x. Remember that our g of x we assigned here was the x squared plus 4x. And then we add that over to the next part. Remember, we need our f of x. We set our f of x as our 3x minus 5. And then we need to multiply that by our g prime. We set that our g prime was 2x plus 4. Now, you could leave it like that depending on what you need, or you could just simplify it a little bit more. But I'll simplify it just because. If you do this, you get 3x squared, 12x plus, and then if you FOIL this, you're going to end up with 6x squared plus 2x minus 20. And then combining those together, you get that h prime of x is going to be equal to 9x squared plus 14x minus 20. So boom, pretty simple. We'll now go over another one. Let's say we want to find, let's say that s of x is going to be equal to, mm, yeah, let's say it's equal to that. And then 2t minus 1, and then 4 plus 3t, and then 1 minus t. Idea is I want to set this whole term equal to f of x, and then this whole part equal to g of x, right? Because if we look back at our product rule, it breaks down into f of x, g of x, f prime of x, and g prime of x, right? And if we just group these together into two, it'll make it much easier. So in order to do that, first we got to take these, and then we got to FOIL them together, right? If you do a little bit of FOILing, we should end up with 6t squared plus 5t minus 4, better spot, and then 1 minus t. Now this is much easier to work with, right? Because then we can take the derivative of each, and then boom, bada boom, right? So if we take the derivative of this one, our first part here, we can say that this is 12t plus 5, and then we can say the derivative of this one is just negative 1. And if you remember, this is our f prime of x, and this is our g prime of x, and then we just apply our product rule. And when we apply our product rule, we're going to end up with first prime of x, and remember f prime of x is that 12t plus 5, multiplied by our g of x up here, which is our 1 minus t, plus our f of x, and our whole f of x function is our 6t squared plus 5t minus 4, and then multiplied by our g prime of x, which is going to be -1. And then you can combine all these terms together, and then the time, it's just going to be this. So s prime of x is going to be equal to -18t squared plus 2t plus 9. And boom. Now, the next part that we got to go over is the quotient rule. This one can be a little bit more complicated because, well, there's a little bit more going on. It's a little bit easier to mess up. But move down here. It states that the derivative, when you have a function that looks like f of x over g of x, when you want the derivative of that, the quotient rule is going to say that you're going to get f prime of x multiplied by g of x minus f of x multiplied by g prime of x, right? All over g of x squared, right? So an easy way to simplify this, how I think of it, is I think of TB minus TB, and then the first one gets a derivative, and the second one gets a derivative, and then your bottom squared. And then what you gotta do here is now let's get into some example problems. Example set 2, maybe? Who knows? But let's say that h of x is going to be equal to x plus 3 over x cubed plus 2, right? What I like to do is how we went over before in the product rule, arbitrarily set one as f of x and one as g of x. You can kind of see it with how it's set up here. One of them's f of x, one of them's g of x, right? So let's say f of x is the top. That's going to be x plus 3, which is write it all out. So it's easier to remember. X cubed plus 2. So f prime of x is going to be just 1, right? Because derivative of x is just 1. And then g prime of x is going to be 3x squared. And now you have all the parts that you need to put it into the quotient rule, right? So h prime of x is going to be equal to, we take the derivative of the first one, which is just 1. Then we need our g of x function, which is x cubed plus 2. And then we're going to subtract this by, and then we're going to take our f of x function, x plus 3. And then our g prime function, which was 3x squared. And we can put double parentheses there. Extend this out a little bit further. And then all this is going to be over our g of x squared, which is x cubed plus 2 squared. And then, of course, you could just put all this together and get an actual function a little more simplified, but for all extensive purposes, I'm just going to leave it like that because that's all the calculus that you're doing. The rest of that would just be some algebra. And so for another example like that, let's say we have another function, h of x, and this is going to be equal to 2x to the fourth plus 2 over x plus 5. Set of more arbitrary values here. This is f of x plus 2, and then the g of x, which is x plus 5. And then we take the derivatives of each one respectively, and then 2 times 4, you get x cubed, g prime of x. You're at that a little ugly. We're just 1. And then you can do like how we did before and just put this into the parts that we remember the quotient rule. So remember, we need our first derivative first of our f of x. Going to get 8x cubed. And then we need our g of x plus 5, and then subtract. We now need just our regular function of f of x. So 2x to the fourth plus 2. This out a little further. And then we need our derivative of g, is just 1. And then we end up with x plus 5 squared for our bottom. And that will give us our whole part for that. And now the next and last part we need to go over is the chain rule. This here, chain rule. So when we go over the chain rule is when we want to find the derivative of a composition function. So f of g of x, for example, right? Let me write this. It's a little ugly. F g of x, right? And what our chain rule says is that if we want the derivative of that, it's going to be f prime of g of x multiplied by g prime of x, right? And so let's have an example set. Say that we have f of x, right? Let's say this is 3x minus 1, and we have g of x, that's going to be x squared minus 1, and we want to find what is f circle g prime. Ooh, yeah. So in order to do that, first off, we need to find the derivatives of our f of x and g of x, right? So I'll just write this right below, make it easier to read. So the derivative of f of x is just going to be 3. The derivative of g of x is just going to be 2x, right? And then we just put this into our quotient rule, right? So we look here, f prime of g of x. What is g of x right now, right? But we also find this for the composition of f circle g of 2, right? And also what we need to remember when it says f circle g, that means the part here, that's the circle part, that's the inner function, right? So say if we did g circle f, that is equivalent to g of f of x. Much different than f circle g, which is g of x. Keep that in mind, because that those will get very different answers. And I think we'll go over that, the difference in the two answers with this question and what it gives. So if we plug into our g of x function here, right? We're going to end up with 2 squared minus 1, right? So let's see here. You do that, you get 4 minus 1, you get 3. So what we're really looking for here is f prime of 3, right? But let's write this out here so we can follow along. So here we did g prime of 2, right? And then we're still going to be multiplying whatever this is, g prime of 2, right? And now we know that g of 2, with what we just did there, was 3. And we're still looking for this. So now, if we plug in, and let's say we want to find our f prime of 3, right? Well, we see that our f prime function here doesn't have an x variable, so it's always going to be 3 at there. And then for our g prime of 2, we go to here, we look, we see that it's 2x, we put in a 2 into it, we get 4. So we get that this is 12. So we can say that now f circle g prime of 2 is going to be equal to 12. Now, I'll compare this to the other side. Let's just put a little dividing line here. Let's say we want to find g circle f prime of 2. what we do here, same thing as before. I'll just rewrite it over here, the derivatives of each one, just so it's easier to work with it over here. And then I guess I'll also write our f of x as well, because why not? So, same thing that we did before, but except now what we're doing this. So, first things first, we need to find f of 2. So f of 2, what we're doing here, times our f of 2. So let's see here. If we plug in 2 into our f of x, what's looking like we're going to get here, we're going to get 6 minus 1, so we're just going to get 5. So now we're looking for g prime of 5 multiplied by f prime of 2. So then we can get those, and respectively, it looks like we're going to get 10 and 3 here. Yep. And so we end up with 30. Right. So if you compare those two things, you get very, very wildly different answers. So that's why you have to be careful when you check which one you're doing, right? Because if you put the composition function incorrectly, like you put in your g prime of x is your outer one instead of your f prime of x is your outer one, you might end up with the wrong answer even though you went through the proper steps. And with that, that's going to cover everything that you need to know about derivatives. And as a brief overview, let's go over everything here for 4.1 through 4.5 derivatives. At first, we went over and talked about what is the formal definition of a derivative, and we said it's here. And this one, either one could be used. But then getting into that, we went over how do we prove whether something's differentiable and continuous, right? And remember that we first have to prove that's continuous, which means we have to evaluate our left limit, right limit, and the value of the point. And then as long as those are all the same, that means that's then going to be continuous. And then we have to check our left derivative and our right derivative and see if those agree. And then if all those come together, then that means that our function is going to be continuous and differentiable. And then we also have to remember that a function has to be continuous in order for it to be differentiable, at least at a certain givable point. And then we went over our product rule, which stated that if we have two functions that are being multiplied together and we want to find the derivative of that whole function, that's just going to be equal to the derivative of f of x multiplied by g of x plus f of x multiplied by the derivative of g of x. And then we went over a couple problems like that, where we were able to have this function that looked like it had almost three different parts, but we were able to combine a couple together and then put it up into g of x and f of x in order to make this easier on us. And then we also went over the quotient rule, where we were able to then say if we want to find the derivative of, say, some fraction, right? We're able to now set the top one, let's say it's f of x and the bottom one is g of x. What our quotient rule is going to tell us is that the derivative of that is going to be f prime of x multiplied by g of x minus f of x multiplied by g prime of x, all divided by g of x squared. Or how I like to say it, the derivative of the top multiplied by the bottom minus top multiplied by the derivative of the bottom all over bottom squared. And then we went through that. We ran through a couple problems where we then set each one as f of x, g of x, and then found the derivatives, and then we're easily able to just plug it in, making it much easier. And then we went over the chain rule, right, where it states that the derivative of a composition function, where you have f on the outside and you have some other part g of x on the inside, right, it's going to be equal to f prime g of x multiplied by g prime of x, right? And then we were able to set as we did before, our arbitrary f of x and g of x into these functions, get the derivative, then plug it in. And then we remember the difference between taking f circle g compared to g circle f, and how they gave us two completely different answers depending on which way we did it. And so for that, that's going to cover everything that we need to know about derivatives.